Could using visual priors improve performance against training from scratch? We examine how using mid-level visual representations improves both sample efficiency and generalization performance. Compared to learning from scratch, using informative visual priors boosts performance, both in terms of learning speed and final reward. We show this by examining three core hypotheses. First, does using mid-level vision accelerate learning? Second, can mid-level vision improve the final performance in unseen environments? And third, what is the ideal visual feature? Will any single feature suffice, or is a set of features necessary? Based on our findings, we propose a generic perception module that provides the benefits of mid-level vision in a way that's robust to the choice of active task. In order to study whether mid-level vision can improve learning visuomotor policies, we sampled three broadly useful navigation-type tasks. First, navigation to a target object. The object is the same over all episodes, although the locations and orientations of the agent and target are randomized. Second, visual exploration. The agent must explore as much of the building as it can in a limited amount of time. And third, a local planning task, where the agent must navigate to a target coordinate specified non-visually using a heading vector. We use representations driven by over 20 mid-level vision tasks, including surface normals, depth estimation, segmentation, and other common computer vision tasks. We take the intermediate activations from trained neural networks and use those features as inputs to our RL policies. These are videos visualizing the actual features on inputs coming from one of our testing environments. We train in over 150 square meters of virtualized space in the Gibson environment. Then, we test in 14 different buildings, completely unseen during training time. Now, we're ready to ask whether visual priors can help support an active task. Agents trained with mid-level vision learn much faster than agents that need to learn tabula rasa. This is true for navigation, exploration, and local planning. Agents using mid-level representations also achieved higher final reward than agents trained from scratch. It outperformed other state-of-the-art representation learning techniques, and this was again true for all of our tasks. The best feature significantly outperformed learning from scratch, but no specific feature performed well on all tasks. In fact, a different feature worked best for each one. Therefore, a set of features should be necessary. This is what we expect. In pixel space, the training and test distributions look very different. So an agent trained from raw pixels will see a huge domain shift between train time and test time. On the other hand, a good feature will warp pixels into a latent space, where the train and test distributions look similar. If the latent space preserves important task-relevant information, both training and test performance will be high. However, if the features are too sensitive to task-irrelevant information, or remove something important, then test performance might be poor. What information is task-pertinent depends on the task, so no single feature should be the best for all tasks. The mechanics of using mid-level features is shown here. The mid-level representation is passed to the RL policy, which uses this as an observation instead of raw pixels. We find, first, that mid-level vision can improve performance, both in terms of sample complexity and in generalization. Second, no single feature can support all tasks. Therefore, a set of features is necessary in order to support arbitrary downstream tasks. Based on our findings, we propose a method to select a subset of features that maximally covers the space of perceptual abstractions while minimizing the cardinality of the subset. Our max coverage min cardinality perception module proposes a combination of features that ensures the ideal one is never too far away from a feature in the set. We provide an interface for efficiently solving this subset selection problem. The max coverage min cardinality perception module outperforms Scratch, improving on the current state-of-the-art. With only 4 features, agents trained with this generic set perform nearly as well as agents using the optimal feature for the given task. Using mid-level representations, policies generalize to the real world. Using curvature-based features, we trained a robot to navigate to an orange cube in simulation. Then we deployed the policy on our real Turtlebot 2 with no fine-tuning. The video shows that the robot is able to navigate to the correct target cube, despite being tested in the real world, in a novel building, and in the presence of white distractor cubes that were not present during training. We also make public an online analysis interface which allows anyone to visualize any of our agents, including all combinations of tasks and features. The tool makes it possible to compare agents side by side, seeing what the agent sees and contrasting performance to baselines. We also provide an interface for comparing the agents quantitatively. Again, all tasks and all features are available. We provide both training and test curves. In summary, we studied whether visual priors can improve performance for learning visuomotor policies. We focused on mid-level vision, showing that mid-level vision can improve sample efficiency, generalization performance, but a set of features is necessary to ensure good performance across tasks. Based on these findings, we proposed a maximum coverage, minimum cardinality perception module. This proposes an optimized set of features that improves performance over tabula rasa learning.